All right, let's get started on chapter 15 here. It's my second attempt at this. I went a couple pages in just a second ago. My pen stopped working, but seems to be working again now, so I'm going to start it over. We're doing section 15.1, double and iterated integrals over rectangles. And so let's take a look at this. The idea is we can basically work our way into the Riemann sum for this by taking a rectangular region and breaking it into a bunch of smaller rectangles. By doing that, we can come across to a picture like this where we would break this rectangular region there up into smaller rectangles like this. And then by doing this, we could go to each one of these rectangles and multiply it by the actual z value in the middle of that rectangle and get then a height. And this would create a bunch of pillars, essentially rectangular pillars that would then add up to be approximately the height there. We can see it better here in just a couple of pages. I'll show you this, but basically you go through and do that. Of course, as we take the number of those rectangles to infinity, the area of each rectangle then starts going down to 0, and we get these infinitesimally small little rectangle pillars that we are adding up. And we get something like this. So this is supposed to be the area underneath that same figure as before, the same kind of curvy figure here, right? We're looking at the total volume there underneath, like underneath this green hood and then straight down flat on the edges. We're looking at that total volume under there, right? And then we come over here and we say, okay, we have that same curve. And if we draw that kind of sketch that curve in, that wavy curve, we can see that by doing 16 of those rectangles, we get a pretty decent approximation. Go up to 64 of them, and you have that same curvy shape in there, and you get a better volume. You come over here to 256, and it gets even closer. So we want to take that limit that n goes to infinity and get the area underneath it. Exactly. This is kind of like finding the area underneath some roof. If you went and took the shape of your roof and included the area inside the attics and inside all the rooms and stuff, that'd be the volume that we are looking for here. And so if we look at this picture, we can see that essentially what we are going to do is do this with two integrations. The first integration is going to be along one direction and then along another. And it's not going to ultimately matter which you do first. But let's say we first start with x being some constant and we're going to integrate along x. So we use that and we find what the value is. Essentially, we find this area right here on the end. And then what we're going to do is move in slightly and find a new little area, a new slice like this, and we find that one and we're going to add it together. Then we're going to go to the next little place and take a new slice like this, and we're going to go all along it, all the way up, making these slices this way, right? Finding the area of each slice and then adding up all those possible areas, and essentially that's going to give us a volume. Just like if we were finding the area of a rectangle, pretend I actually drew a good rectangle there. I guess I could use this tool, right? I would, oh my gosh, that was really bad. If I came along and I drew a rectangle and I wanted to find the area, I would essentially find this length plus this length plus this length plus this length plus this, and I just go through and add them up. That's the base times the height. If I wanted to turn this into a volume, I would then take the area of this end that I found and multiply it through, right, by the depth of it, right, which would be essentially, multiplications are repeat addition, which would be essentially going through and adding up all these slices, right? I'd have all these slices of these areas I was finding. It just happens to be pretty easy because all the slices are exactly the same. Here, though, each slice has a different area. But to find the area underneath any single slice, I can just do that with integration, right? So if I have, this is part of some other curve, right, like this. Ooh, I still have it on the straight line thing. This is a part of some other curve that comes along there in the x equals 2 plane. Then I can just integrate underneath that curve and find that area, right? And so then all I have to do is take a little step in the x direction and integrate over underneath that next curve that occurs, and then take a little step in and integrate on that next little curve, except I'm limiting myself here to these bounds from here to here, right? There to there, there to there. So I'm starting here and integrating to there. It's not a very good color, I can't see that. starting here and integrating to here, and so I'm getting that area, and then I'm starting here and integrating to here. And so you're just going through and adding up these slices. So you have to integrate two ways, both through x and then through y, or conversely, you could integrate the other way. It doesn't matter if you integrate through x and then through y, or through y and then through x, because we can do this the same other way. We can take these slices here and then take the next slice and then the next slice and then that next slice and the next slice, and just keep integrating. Each individual integration gives us the area of one slice, and then we integrate up all those areas of those slices to get the total volume here. And so whatever shape we happen to have, right, we have some crazy weird surface that we're looking at here, we're essentially just going down and finding the area underneath it. Much like, or the volume underneath it, sorry. Much like we would have done for regular order integration, anything that goes below one of the planes into the negative regions is going to be like a negative volume, and therefore you could end up with a total volume of 0 for something that doesn't look like 0. So you have to pay attention to above and below planes. So if this extended down into the negative z direction, then we would be getting negative volumes for it. Just like if it's above in the positive z direction, we're going to get positive volumes for it. But we're basically looking at the volume. So it's very square and flat on the bottoms and on the sides, but on the top it's some surface. And here's how we can do it. Essentially, this is saying if we integrate over a rectangular region R and we integrate our function of x and y over that area, we can replace that area right there, this dA, with a, dA is dx times dy, and then we integrate dx from a to b, a to b, and we integrate dy from c to d, which will be equal to, we can swap the order as long as we also swap the integration order as well. So we put dy first, and then in that case, we get the same thing if we integrate dy from c to d, and then integrate dx from a to b. So you work kind of inner to out. So you would do this integral and then this outer integral, okay? And that's the way you would do that. And either way gives you the same answer. So let's take a look at an example here. We want to calculate this volume underneath this square region underneath that surface there. And we're given that the function is 1 minus 6x squared times y. And the rectangular area underneath it that we're interested in is from x 0 to 2 and y negative 1 to 1. So if we use this theorem, we can integrate on x from 0 to 2. Right there, we're going to do that inner integral first. And then we do the outer integral for y from negative 1 to 1. And so when you do that inner integral, you just go ahead and integrate it with respect to y. The integral of 1 just becomes x. The integral of 6x squared y becomes x cubed over 3, so it becomes 2x cubed y, which is what we have right there. And then you evaluate that from x equals 0 to x equals 2. And plugging in 0 and 2, you end up getting this 2 minus 16y. And then in that case, we're then going to go ahead and take the other integral, which is to integrate it over y. And so then that's just a very typical integration over y from negative 1 to 1, and you get 4. If you look down below, they reversed the order. They did y first. So you did this inner y integral first, and then did the outer dx integral, integration over x, and you still end up getting the same answer. So it won't matter which order you do those in. So here you can see another picture of this. Again, what you're doing is you're coming along and you're saying, all right, I'm going to find this area here, and then I'm going to find its area using integration, and then I'm going to step in a little bit and I'm going to find this one's area, using integration. And I have basically two integrations. I'm integrating, I'm integrating to find each of these areas, and then I'm integrating this way to add up all of those areas, because that's what integration ultimately is, right? That's what this symbol is. It's an elongated S that stands for our infinite sum. So that's how we add up all the slices. So you're either slicing it in the x direction and then finding those areas in the x direction and adding them up over the y, or you're slicing it in the y direction and adding them up through x. Just depends which one you do first and which one you do second. All right, here another example. Find the volume of the region bounded above by the elliptical paraboloid z equals 10 plus, that should be x squared 3y squared. So that should be x squared plus 3y squared. Okay, so 10 plus, so that's what that equals. We can ignore that. And then, and below by that rectangle. So we're finding the area underneath it. So this might be, maybe this is the volume underneath a certain section of a tent or a tarp or a carport or something like that, where this is the roof of it and we want to know what's the total volume underneath this carport or tarp or whatever happens to be there. And you would do that by doing this integration. And so we can set this up where we are integrating double integral here over the region R of our function, which is 10 plus x squared plus 3y squared dA. That's going to equal our integral, and we can do either x or y first. So if we do x first, it'd be from 0 to 1, 10 plus x squared plus 3y squared dx, and then we're integrating y from 0 to 2, and so dy. And so do both of those integrals, plug in your limits there, and you should be able to come up with what the answer is there. But I'll leave that for you to finish up and try. Okay, and that's it. That's it for this section. We'll get into some more, multiple integral stuff here coming up, but that's it for right now. So thanks a lot.